Good morning, Algebra 2. This is the last lesson of the year. So lesson 110, we are going to be graphing log functions. So something to remember is that logs are the inverse of exponential functions, and we're going to use that knowledge to build their graphs. So I've given a few examples. So here's the rule. And so like log base 4 of x equals y. The inverse would be y equals 4 to the x. Log x of y is the same as 10 to the x equals y, because there's an invisible 10. So we're going to do an example. We're going to graph log base 2 of x equals y. Now, in order to do that, I'm going to build the table of what I know. So for example, -2, -1, 0, 1, 2, I could even go on to 3 if I wanted. So if I was to fill in this table, 2 to the third is 8, 2 squared is 4, 2 to the first is 2, 2 to the 0 is 1, 2 to the -1 is 1/2, and 2 to the -2 is 1/4. Now I think it's easier to make these a decimal, so this is actually 0.5 and this is 0.25. So when I go to graph log base 2 of x equals y, I simply flip the table over. So, and this is how I do it. If you don't like this method, I guess you could use a calculator. But I'm simply going to flip the table over. So my y values are now my x values. And my x values are now my y values. And so I'm now going to use that table, sorry, I was looking for my ruler, to graph. So I'm going to make sure I leave room for +8 on each axis. So this would be 4, 8, 4, 8. So here's x, here's y, here's -2. You know what, I'll move this. Here's y, here's -2. So in blue, my exponential function is -2.14, 0.5, 1, 2, 4, 8. Those are my points. And look at this nice exponential. Now, an exponential, it'll never go below 0. Now, my log is the complete reverse. So 0.25 and down -2. 0.5, -1, 1, 0, 2, 1, 4, 2, 8, 3. And so it does feel really strange to graph because we're not used to graphing decimals for x. If you'll notice, those are inverse functions. Now, inverse functions should be a reflection, which the book goes over, of y equals x. So if I was to graph that line, y equals x, you'll see that these graphs are perfectly reflected across of it. So this is y equals x. Y equals x just means 1, 1, 2, 2, 3, 3, 4, 4. They always equal each other. But notice they are reflections across. Now we're going to do domain and range. So the domain of my exponential is I'm sorry about that. X is all real numbers, but range, if you'll notice, my range isn't going to go above where y is 0. So y has to be greater than 0. Now, I'm simply going to switch my domain and range for my log function. So my domain is now x is greater than 0, and y is all real numbers. So remember the red function, this is my log function. So that is what we're going to do in the next couple lesson practice. You may also use Desmos to confirm your graph. Remember on Desmos, so Oh, sorry. I have to dim my screen for you to be able to see Desmos. So on Desmos, if I put y equals, and then I have to go to functions, I'm going to guess it's a miscellaneous, and I have to hit log base a, so I need to hit log base 2, and then in parentheses x, and here is our graph. And so you can click on it for points, but there's 8, 3, there's 4, 2, there's 1, 0, but it should support the graph. They're even both in red. Okay, so you can also use Desmos to verify your graphs. But I'm going to do it by hand in case you guys move on to trig. So lesson practice is on page 766. So in part A, they'd like us to graph f of x equals 3 to the x and f of x equals log base 3 of x. And so I'm going to do the same thing. I'm going to do this in blue. And I'm going to not do as many because these get really large. So I'm going to do -2, -1, 0, 1, 2. So 3 squared, which would be the 2, is 9. 3 to the first is 3. 3 to the 0 is 1. This is 1/3. This is 1/9. Now for me, I think it's easier to make these a decimal, right? So we know this is 0.33. So 1/9 is 0.11. So now I'm going to flip. Remember, I'm going to flip it over for my log. And f of x, sorry, you can make that f of x, it doesn't matter. So my y values are now x. And my x values are now my output, or my f of x values, y, whatever you want to call them. And now we will graph. So I need to leave room for 9. So 4, 8, and this is x. 4, 8, this is y. -2, -2. So put some numbers on your graph, even if you only put 1 on each. So 1 on the x, 1 on the y, so I know what your scale is. So in blue, I've got -2 and 0.11, 1/3, 1, 3, 9. So if you'll notice, it looks very similar to the one I did with you. It's just more steep. And then now reverse it. So 0.11 and -2, 1/3 and -1, 1, 3, 1, 9, 2. And I usually have to tilt my paper, and you can do the same. So let's start with, remember the red one, this is log base 3 of x. Okay. So domain of exponential is all reals. Range is y is greater than 0. And then I simply switch for the log function. My domain is x is greater than 0, and my now range is all reals. Beautiful, beautiful, beautiful. So moving on, we're going to do B and C. Again, when in doubt, you may use Desmos for your graphs. Sorry, I'm just going to my notes. So in B, they asked us y equals 12 times the log of x, and to graph y equals -12 times the log of x. Okay, so the 12 here, right, there's an invisible base of 10. And so the 12 here, the positive 12, is a vertical stretch, meaning it affects our y values. And the negative 12 is a reflection across x, and it's still the vertical stretch from the positive. So there's a couple ways, right? I'm going to do the inverse, which is 10 to the x equals y. Now these numbers are really big, so I'm only going to use a few. So negative 1, 0, 1. This would be 1/10 or 0.1, 1, 10. Okay, so log base 10 of x equals y would be 0.1, 1, 10, negative 1, 0, 1, right? So now I'm going to transform that one to be y equals 12 times the log of x. So I am only affecting my y value. So this is 0.1, 1, 10, but I'm going to multiply these y values by 12. So negative 12, 0, 12. And then finally, y equals negative 12 log of x. The only difference, it would be these values times the negative 1. So this would be 12, 0, negative 12. X values remain the same because it is only affecting our y values. So I'm going to grab my ruler. Now this graph is going to be quite large because I'm up to 12. You're more than welcome to change your table, but I feel like it takes, and I'm going to actually change, but I do still need to go from 12 to negative 12. So 12, say this is 8, 4, then this would be x. So 4, 8, 12, negative 4, negative 8, negative 12. Okay, so I've got my x value, and here's my y value. So in blue, I have 0.1 and I gotta think about this. 0.1, sorry, and negative 12, 1, 0, and 10, 12. So this graph is very tall. That's because it was vertically stretched. So there is the y equals 12 times the log of x. This one has been reflected. So this point is now up here. This point is the same. This point is now down here. And so there are the two graphs. All right, moving on to part C. Let's see if I can get this all on one table. Now for, actually I'm going to have to turn the next page. I'm actually going to do this next one slightly different. I am going to use my calculator for this one, if you'd like. You don't have to, but we can. So here we go. Sorry. Part C, they'd like us to compare the difference between 5 times the natural log of x and y equals 5 times the log of x. Now this has an invisible base of e, and this has an invisible base of 10. So we can use my method if you prefer. If you don't, we don't have to, but or we can use a calculator. Sorry, I'm trying to think what's easiest. So For this one, I have e to the x equals y, and then this would transform into, I'm trying to think of the easiest way. Let's just build our table. All right, so let's say I plug in decimals. So let's say I do 0.5. That's not going to work. I want to know, well, I just don't want to do a million transformations. Let's just build the table. But make sure you use decimals. That's the only thing I was trying to. So let's say I do 5 times the natural log of 0.25. So I'm plugging in 0.25. And I get negative 6.9. Okay, now I'm going to do, let's say I do 0.5 times the natural log of 0.75. I get negative 1.4. Say I try 0. And that doesn't work. Sorry, that would be before these decimals. I'm so sorry. 1. Huh. And then 5 times the natural log. Let's do, I don't know, 6. And I get 8 point. We're going to go ahead and round that. We'll just do 8.9. Now for this one, oops, I'm going to use the same values so that we can compare, okay? So I'm going to plug in the same numbers for x so that we can compare the difference. You know what? Maybe I should have kept this at 5. Let's try this at 5. So it's slightly smaller. Again, you can put this in Desmos. It just wanted us to compare the difference. So now I'm going to find this one in red. So 5 times the log of 0.25, I get negative 3.01. 5 times the log of 0.75, and I get negative 0.6. 5 times the log of 1, and 5 times the log of 5. So if you notice, these values are smaller, but that's because the base of, like, this is 10 to the what, so the exponents are going to be much smaller. And then you would graph the two. I'm trying to leave room for everything, sorry. I think I have room. All right. So in blue, I have 0.25 and negative 6.9. So it's almost 7, so this would be 6. 0.75, which would be here, and negative 1.4. 1, 0, and then 5, and almost 8.1. So I'm going to there's blue. And red, 0.25 is only at negative 3.1. 0.75 is negative 6, 105 is at 3.5. And then you can talk about like the greater base is smaller y values, up to you. Last one, and I wanted to fit that on there, are the effects or the train. If I have y equals the natural log of negative x, and you can use Desmos for this. And I'm going to compare this to the parent function y equals x. Okay? And I'll move this down for you. Sorry about that. And we'll just use Desmos. So if I have y equals, under miscellaneous, the natural log of x. So what happens to this when I put a negative inside? So I'm going to do the next one, y equals the natural log of negative x. Okay, so notice what this one did. It reflected it across y. Okay, now this one's still negative, but now what happens if I put a negative 5? So y equals functions, miscellaneous, natural log of negative 5x. All right, so notice that it's still the reflection, but the values got higher, so we call that a vertical. You can either put greater y values, or you can put a vertical stretch by 5. So we could probably guess, right? It's still going to be reflected, but this is going to have a vertical stretch by 10. And that completes this lesson.